All right. Okay, guys. So hopefully this recording finds you well. I'm sorry I didn't get a chance to record this before the spring break. So it's kind of making it to you probably quite a few days late. Hopefully you'll get a chance to take a look at this. Let me first start by talking about the summary of what we covered last time so far. So far, let's see. Let's do a summary. Is that what we did last time is that we showed that the electric field is a conservative force. That means that, I guess the way to look at it is if a particle is working against or with an electric field, or if an electric field is working on a particle, regardless of the path that that particle takes, the amount of work that the particle takes between any 2 points along any two paths, it stays the same. So that's kind of in a nutshell. Because it is a conservative force, basically it allows us to define a potential. So again, if you guys remember, if this was not the case, then we would be left in a pretty bad situation, that if we wanted to see how a particle was reacting to this electric field, at every point we would have to calculate its velocity, then figure out the acceleration it would run into, then go incrementally ahead in time, find the new position of the particle, and get its new velocity, new acceleration with respect to the electric field in that new position, or the force on it in that new position, and so on and so forth. And that would be the only way we could define its path in an electric field under an electric force. But because it is a conservative force, all we have to worry about is the initial kinetic energy and the initial potential energy, and then we could figure out where, if it ends up in a place, what its potential energy is, and then what its new kinetic energy will be. So anyway, what does that mean sort of from the standpoint of the electric field calculations? It means that the closed loop integral of the electric field, dot product of it with the direction of travel along this closed loop, is equal to 0. So this is essentially the definition of a conservative force. So essentially it kind of means, if I was going to draw it a little bit, hopefully I'm drawing it correctly. This is sort of giving it to you guys in a nutshell. If you take any 2 points, A and B, and you have a particle taking any two paths between those 2 points and back, so that's what we mean by this closed loop. If you do the electric field, dot product of the electric field, the direction of travel, it's going to be 0, meaning that if you travel to that point, come back, basically this integral is going to give you a 0 value. It's a definition of a conservative force. Now, also, I guess we know that, before I get too hand wavy, this is of course the electric field, which is not quite the force. The force is Q times the electric field, with Q being the charge that's moving around. But because the charge is just it's not a vector, it's not a variable, etc. The charge that's moving around. If we show that this integral ends up being 0, we've also shown that q times the integral is also equal to 0, and this is the force. Okay. So since we've shown this, it means that we can define something called a potential. So we call that V for the electrical potential. Now you got to be careful. That's not the potential energy yet. This is the potential. So we can, because the electric force is a conservative force, we can define a potential so that the kinetic energy of a particle, so this was small v, the velocity, that's 1/2 mv1 squared, is the initial kinetic energy plus q times the v at location r1. So this is the initial potential energy. This is the initial kinetic energy, is equal to wherever, let's say we want to look at what it will do once it's another location in space. It's equal to the kinetic energy at that location. So at the new location in R2 plus the potential energy you'll have at R2. So this is U2. So again, V is the potential, U is the potential energy, and it's basically multiplying Q by this potential. Okay, so we can do this. So this is very analogous to the gravitation. So kind of as a reminder of what gravitation would look like if you had some height above ground. So this is, let's say this was some hill or something like that. At each point on this hill, you would face a potential energy. You'd sort of get a potential of GH, and then you would have a potential energy. This is again the gravitation analogy of m, your mass times the GH. Okay, so think of V, the potential, as being this GH. So G is sort of a gravitational constant, H being the height, and then the charge would be analogous to the mass. Okay, so because we don't know if there's an elephant up here or a mouse, each one would have a different potential energy if it's sitting here. Okay, so again, we define a potential, and then depending on how much, sort of an electrical analogy, you define a potential, and depending on how much charge is sitting at that potential, it could be a coulomb, it could be an electron, which would be 1.6 times to the minus 19 coulombs. They would have different energies. Okay, so so with this, given that we have this equation, the other thing we can write is we can write that the voltage or potential difference between R2 and R1, which are two different locations in space, is minus the integral from R1 R2 of d E dot dr. Okay, so again, I'm just sort of going over the high level aspects of what we covered and trying to give some sort of color to what we have. So this is the potential in some new location, or in location R2. location R1, you do the integral from R1 to R2, and then E dot dr, and that's a difference in this potential. And if you wanted to define the difference in potential energy, you just multiply Q by all sides, I guess. So one thing I wanted to talk about a little bit about, like sort of a feel for what does this minus sign mean, which, you know, don't forget, it's always this minus relationship between the electric field and the potential. And one way to, I guess, to look at that is that the minus sign means that you're doing work against the electric field as you're going from R1 to R2. Okay, so it's sort of like so I guess that's how you look at it, but you know, it comes out of the math, but the way you can look at it is you're doing, you know, the electric field is pushing you in a certain direction, but you're working against that. So you would have this minus sign. Okay, so if you look at a particular, you know, charge coming, you know, sometimes you want to define the, you know, by definition, the potential is a difference between 2 points. Okay, so you really can't tell, you can't say something about this will have a certain potential. But if you're bringing a charge from like infinity into a point in location, so if you had some v sub r minus v at infinity, that would equal to minus infinity to r e dot dr. You would, by convention, like this v infinity could really be anything, because, you know, we're subtracting two values together, so you could have a constant sort of for both. Okay, so by convention, we're going to say that v at infinity is 0. And so if we choose to, again, because really what we care about is a potential difference always. So if we make v at infinity, we could have made it a constant or sort of a value, and then basically call the potential at any other point, the potential at that point minus that constant. Okay, we could do that, but just to make life easy for ourselves, by convention, people have made the potential at infinity equal to 0. So you can talk about, you know, when you're sitting in the lab and talking about a voltage of, you know, you've just measured a voltage of 10 volts in your potentiometer, you're kind of saying it's 10 volts with respect to this, you know, infinity, which is by definition 0. Okay, what else do I want to say? So now if we do, let's say we have a single charge and we want to do this integral for a single charge Q. So I'm gonna do this integral for it. We would get v at r minus v at infinity is equal to q over 4 pi epsilon naught 1 over r. Okay, where r distance from Q. In other words, I didn't really say this well, but let's say you had a charge Q sitting somewhere, and you wanted to figure out, you were bringing another charge from infinity somewhere here in the presence of only this charge Q. Okay, so we would put it in different places R, where R is this separation from this Q sitting here. Okay, we would end up, so basically what this Q is doing is defining the electric field of, in other words, if you were doing this against the electric field of a point charge, what you would get from that integral is Q over 4 pi epsilon naught 1 over R. Okay, which is this, the potential for if you're moving in the electric field of this point charge. Now this looks a lot like, especially after spring break, this looks a lot like Coulomb's law, in the sense that, we got this familiar Q over 4 pi epsilon, and then we have this 1 over kind of R function, but there are definitely differences. Well, for one, Coulomb's law, it was, so the differences are there's no 1 over R squared term. Oops, I'll make this 1 over R cursive. No 1 over R squared term. Okay, so that's one. And two, very importantly, there's no vector. So basically, potential is a scalar, which means you're just dealing with a number and no direction. And if you wanted from there, well, I'll talk about how to get there from there to a direction of the electric field in a second here, but that's one of the nice things about dealing with potentials versus electric fields, is at least we don't have to worry about vectors for a bit. Okay, so those are the main differences of a potential with Coulomb's law, which defined, force and electric field. And then but fortunately superposition still holds. So if you have lots of charges, the potential is the sum over all these charges of the different charges over 4 pi epsilon naught 1 over the absolute value of R sub I minus R. So basically the distance from the new charge would feel respect to distance of any one of the old charges sitting around. Okay, so that's Ri minus R. And again, notice this is very important in terms of the potential, is there's no vector. It's a scalar. Okay, so then from there, if you want the E field now, basically you do this grad. All right, so guys, so if you want to get the electric field from the potential, what you do is you basically get this function of grad of the potential, which means basically you take the derivative of the potential with respect to x and multiply it by this I vector. So that gives you a vector in the x direction for the electric field. So that gives you a component there. So now you've gone from a scalar to a vector. And then you add plus, or I guess you just be minus. Let me just not get too smart here. Minus j dv dx. Okay, so you'd get the x direction component of the electric field would be the minus the change of potential with respect to x, and the y component of the electric field would be the minus change in potential with respect to x. And then if you had, if you were in 3 dimensions, you would have minus, k vector dv dz, etc. But we're just to make it a little bit easier, we're just gonna talk about xy, but basically that's how you would go from electric field. You'd get back a vector from this scalar potential. Okay, so that's kind of a summary of potential energy and the relationship between potential and the electric field. Okay, so let me now just take a step back and talk about something that I think talked about last lecture that I need to make a correction about something I said in last lecture. So this is a correction to to last lecture. Okay, and so I was talking about doing this, talking about work in a conservative under conservative force of electric field. And what I said was that if you had the electric field lines, so if you had two directions of movement, so let's say you were going to get from this point to this point, going in this path, it would be the same work as going from this point. He took this other path to get there. And so the idea was that this blue curve would have, E dot dr along this blue curve, and that this would be, because it's this was in a point, under a point charge, away from a point charge. So this E dot dr was E is radial. So E dot dr just calculates this electric field times this distance. And then because the electric field's radial, any radial movement here would give you 0 work. This would give you 0 work, so it'd have 0 work. This is angular movement. So this angular movement gives you 0 work. This angular movement gives you 0 work. So if you were going to go down this path, this would be 0 work. You would, because this is radial completely, you would have the same work as this. So 0, same as the other path, and then 0 in angular work again. And so saying that this is the same as this work. So essentially the claim was that blue path, movement along blue path was same work as along green path. And this is still correct. So I'm talking about what the example was again. This is again sort of point charge in a electric field caused by the point charge. And so this is still correct. So this is still a correct statement. But then I further made, where I went wrong in my claim, was that I further claimed that if you had sort of any path, any meandering path, you could that you could just break this down into a bunch of like radial and angular components. You just break it down, and that if you made these radial and angular components small enough, tiny enough, it would be the same as movement along the path. And that's kind of the incorrect statement I made. And let me show you what I mean. What I mean is that, let's say if you had, or show you how this is clearly wrong, is if you had a triangle of side 1, this the sort of hypotenuse would be value of square root of 2. Whereas if I sort of divided this path into a bunch of little steps, bunch of little steps like that, you could show that the sum of the movement or the distance along those paths isn't really square root of 2, so it is actually 2, not square root of 2. So, it's easy to say, I guess, that, hey, I'm going to make, if you look at this thing from far away, they kind of look the same. But because because you're dividing something into a bunch of infinitesimal steps, doesn't necessarily mean that the sum of those infinitesimal steps are going to be the same as what you divided up, because each one of those infinitesimal steps could have a finite error or a finite difference. And so, because they're infinitesimal, there's going to be sort of an infinite number, a very large number of them, meaning that that error summed up could still give you to a significant difference between what you broke down and the value. And again, this is sort of a simple example of how that's the case. So what I should have said, though, so let me tell you what I should have said, and let me replicate this this path that I'm talking about here. Let's try to draw it sort of in a bigger, something like that, I guess. So this would be a radial, and this would be, let me. So this would be a radial. This will be some meandering path, okay? And if I blew this up further into small components, what I should have said is each one of these small components, so if I take any small component here, it would have a direction along the electric field. So because it's along the electric field, so this is sorry. So let's say this step that I'm drawing here, I'm blowing up here. So this guy is an infinitesimally small step along this meandering path. Okay, so that in this small step, for this small step, we can say that the electric field is constant because it's a very, very tiny step. Okay, so that's in the radial direction then. In the radial direction, you would have E dot delta R, which is how much you moved. So let's say I'm taking a real tiny step here in the radial direction, and then comparing it to my meandering path. So this would be the radial component. Okay, and then here's, say, my meandering path. I should have said that this component is really E of R times dr, absolute value, sorry, that's the absolute value electric field, absolute dr, times the cosine of theta, which is the angular component between the meandering path and that path. So what I should have said is that you don't necessarily need to break this meandering path down to radial and angular components. But if you do go at a slant away from the radial, the amount of work depends on how much you travel with respect to the radial direction only. Okay, meaning that it's the amount of work that this is the small component of my meandering path. The amount of work is only going to depend on how much I worked, sort of this dot product between the electric field and the direction of travel. And so that gives me this cosine theta angle between them. So it just only means that it's the amount of, so again, instead of saying that I've divided, this is a subtle difference, maybe it's not so subtle, but what I initially said was that you can break this into radial and angular components, this meandering path, sorry. How do I do this? It's hard to almost show it here, the way I drew it. Radial angular components, that is wrong. But basically what I should have said is that the work only depends on the radial component, which is the dot product of the direction along that little bit of the path and the direction of the electric field. Okay, and that's what the E dot dr dot product is doing. It's just saying it's, we're talking about the integral of E dot dr. So this E dot dr is just saying that all that matters is the direction of travel along the path of the electric field. And that's why, regardless of the path you take, you always end up getting the same answer. Okay, not because you can divide things into radial and angular paths. So kind of a subtle difference, but the result is still the same. But just wanted to clarify that because it was kind of a wrong statement about what it was. And then the second kind of correction or thing I wanted to add was I forgot to talk about units. Okay, so the electric field, the units are given in newtons per coulomb, and V is the work done on a unit of charge. Okay, so that's given in terms of joules per coulomb. Okay. And we could have left it at that, or people could have left it at that, but they've made basically this joules per coulomb is basically called a volt. Okay, so if one way to think about that is if you had, say, a 4 volt potential difference between 2 points, and you took a coulomb of charge from one point, from one of those points to the other points, you would have needed to put in 4 joules of work. Okay, so that's kind of what this joules per coulomb means. But again, it's the term, it's volt is the name, but we shouldn't forget that it's really talking about work that a unit of charge would have to do to get from one place to another, and it's basically relating potential energy to kinetic energy. Okay, so let's see. So that's all the stuff from last time. So now let's talk about new stuff. So first, let me talk about what new stuff I'm going to talk about. This is all all of it has to do with the advantages of using potential. I guess advantages compared to thinking about electric fields or electric force. Okay, so let me first list all the advantages of doing that, and then I'll talk about each one of them in detail. So the first one is conservation of energy. And that's, we did all that work showing that it was a conservative force, and so we could use conservation of energy. Then sort of the computation of the electric field. And then I guess third one is visualization, say potential maps, I'll call it. Okay, maps. Maps. All right. So first, let's talk about this conservation of energy. And this is really what we did, a ton of work, a lot of math talking about. But basically, okay, guys, sorry, my recording keeps getting interrupted for whatever reason. But what I was about to say was the new stuff we were talking about. And I was going to sort of go more into the conservation of energy basically the overall idea is that we're going to talk about the advantages of thinking in terms of potentials or voltage or V as opposed to electric field or electric force. So they're both useful, but here are the advantages of thinking in terms of a potential. Well, the first thing is just talking about conservation of energy. We talked about this quite a bit, and it's a real important topic, and it makes life really easy. So if you didn't want to use this concept, so let's go back to, again, our gravitation analogy and thinking about a roller coaster. So if you think about a roller coaster sitting at the height of where it's going to be, and before it started moving, you could think of it as having a certain potential energy and zero kinetic energy. And then if you then looked at it at some other point, after it started rolling and did a bunch of stuff at some new height that it ended up in, and now you can, just from that new height, that new potential energy that it has, you can calculate its kinetic energy and therefore its velocity at that new location. So it's a really a huge shortcut using this conservation of energy methodology, because the only other way to do it would have been at each point between when you were starting to roll and the new position. At each one of those points, you'd have to figure out what your new velocity is, the acceleration that you'd be feeling, and sort of a new position. Then you go to that new position, and then you recalculate a new acceleration, a new velocity, and then get a new location, and so on, and incrementally do that for every point in between these 2 points, from your starting point and the ending point. And that's a much more tedious and long calculation. So with the conservation of energy concept, you can skip through all those intermediate steps and just calculate the potential energy and initial kinetic energy and the final potential energy and final kinetic energy. And in particular, if you want to find the final kinetic energy, it's really easy to find it from that, using this sort of conservation of energy. The second thing is that using this potential makes it a lot easier to calculate the E field. Okay, in most cases, it's easier to calculate the potential than it is to calculate the E field. So let's take a look at why. And I was sort of sketched out this example that we'd used before of a dipole. I think we did this several weeks ago. And so we had a dipole, a minus charge and a plus charge of equal value sitting on the x-axis, a distance of 2a apart. And we were going to find the electric field. And if I remember correctly, we only calculated at a couple of points, one along the x-axis and one along the y-axis. And because it was just, would take a long time to calculate the electric field at other points. But if you wanted to calculate the electric field at other points, what you would do is you would find the vector component of the electric field caused by this plus Q charge. Let's say you want to calculate the E field here. You would calculate this electric field. You would calculate the electric field caused by the negative charge. And then you would do a vector summation of the two, and you would calculate the total electric field at this point. And then you could do this for any point along here. Okay, so basically we had the procedure to calculate the electric field at any point, but it's difficult. You guys did it, your homework, tests, etc., because you've got to figure out you're dealing with vectors essentially. Okay, so that's what makes it, you can map the electric fields everywhere, but you're dealing with vectors. Okay, but if you're working with potentials in terms of voltages, what we can do is we can figure out the potential at each point. And remember, the potential is not a vector, it's a scalar. So you can just basically, the potential at each point for each one of these charges, those are just two numbers, okay, one for each, and you can just add them. And numerically straightforward, add them, there's no vectors. And then if you want to figure out the electric field afterwards at that point, you basically take the derivative of the potential with respect to x, and that becomes the x component of the electric field, and you take the derivative of the potential with respect to y, and that becomes the electric field component in the y direction. And then basically, that becomes your electric field at that point. So again, in a lot of cases, we'll see some cases that's not the case, but in a lot of cases, it's easier to calculate the potential first, and then from that, get the electric field. Okay, so let's see how that works. So let's look at the same same problem of this dipole in terms of potentials rather than in terms of electric field. So let me redraw this thing. Whoops. And I've got a plus Q sitting here, and then a minus Q here. And let me let's say we want to figure it out at this point somewhere here. I call that R plus. So I'm not going to deal with vectors actually. That's good. So I'm just going to do R plus. And then this guy, let's call that R minus. So R plus is the distance of this point we're using to the plus charge, and R minus is that distance to the minus charge. And okay, so the voltage there is Q over 4 pi epsilon naught 1 over R plus minus 1 over excuse me, R minus. Okay, so that's the potential at that point, which is equal to Q over 4 pi epsilon naught R minus R plus. over r plus r minus. Okay, so that's what the potential looks at every point. Okay, now let's see if we can sort of simplify this. If you look at this from a distance, okay? So trying to simplify this equation a little bit as an approximation. So imagine if we were far, far away from, so if let's say the plus q look like this, and the minus q look like this, and we were out here looking at this, at these two, so far away. So basically r plus, r minus, and then this is 2a. So basically r plus or r minus are much bigger than, much larger than 2a. Okay, so how can we simplify this? So looking at the denominator, okay, basically if you're in such a, well, generally in terms of the denominator, if you look at the components of this denominator here, so looking at denominator, questions, how can we simplify that a little bit? Well, we can look at r plus times r minus. Sorry guys, my dog is barking there. Let me close the door here. So r plus times r minus, this denominator would look like, again, far away from this dipole pair, it would look like r squared if I defined, let me just say define r as the distance from the origin. So that would look like r squared times a bunch of other terms, a over r plus a squared over r squared plus dot dot dot. So if r plus or r minus are much bigger than 2a, or much bigger than a really, then this r plus times r minus is approximately equal to, so let me copy that over. Basically what happens is, if that's the case, then notice that these terms basically go away, because we're saying a is much smaller than r. So these terms would all be approximately 0, so we would get approximately r squared on the denominator. Okay, so now let's see what happens in the numerator. So that's the denominator. In the numerator, we have r minus r plus. And we could say, well, look, we said r minus, we've said r minus r plus is much bigger than a, but we haven't really said anything about the differences between them. So we can't just say that's going to be 0. We have to do a little bit of more work. And what we do is, there's a little bit of hand waving here. So get ready for my hand waving here. So what happens is, if you draw an angle, sort of a line between these guys here, you can think of this distance as being r minus r plus, because that's the difference between those two lines, the r plus and r minus, this length here. So if I call this angle here, if I call it theta, Okay. Basically, I can say that, so it'll look like that. So I'm going to say that R minus R plus, oops, sorry, it's pretty ugly. R minus R plus is equal to 2a cos theta, because this is 2a. I want to figure out this distance. This is R minus R plus. That's equal to 2a cos theta. Okay? So like come up with that. So cos theta, so let me write that over here. So R minus R plus is equal to 2a cos of theta, or cos of theta is R minus R plus over 2a. So coming back to the V for the dipole, okay, so I said that's Q over 4 pi epsilon naught R minus R plus over R minus times R plus. So replacing these, we end up with Q over 4 pi epsilon naught. We replace the top part with 2a cos theta over, and replace the bottom, again far from the dipole, with just r squared. We did that here, and we did it sort of here. Okay, so again, remembering that the dipole moment is, if you guys remember, we defined this concept called dipole moment, which is P, that's equal to 2AQ. So that's sort of this guy. So that's equal to P cos theta over 4 pi epsilon naught r squared. Okay. And now so far so good. Okay, so this is the hand wavy part of this. I'm going to make a claim that when you are far away, let's see, that in that case, when you're far away, so that this, if I call this theta prime, okay, so this is the angle from the origin, that far away theta prime is equal to theta. Okay, so again, this is saying that if you're far away from this point, this angle and then this angle are about the same. So this is, I'll call that a claim that far from dipole theta prime is equal to theta. So again, let me draw that. So this would be the plus Q minus Q. This would be the point of interest. And this would be the distance. This is the origin. and this is theta prime. So I'm saying that if you move far enough away from the dipole pair, theta prime is equal to theta. And therefore, cos of theta is equal to x over r, if this is r. Okay, so I'm going to plug that in. So V is P cos theta over 4 pi epsilon naught r squared is equal to P x over 4 pi epsilon naught r cubed. And r is square root of x plus y. So this ends up being P x over 4 pi epsilon naught x plus y to the 3/2. And so this is the potential at sort of any point far from, so this is potential any point let's say far enough. Doesn't have to be so far, it just has to be, the separation of the dipole, there's 2a and you have to be sort of significantly further than that, but at any point far from dipole is this guy. And then once you have this value, basically you can calculate, once you have this equation, you can calculate the electric field at any point, at any point by calculating the derivative of the voltage of that. The x component of the electric field would be the minus the derivative of this voltage by in respect to x, and the y component of the electric field, these are vectors now, is times I, and the y component of the electric field would be minus dv dy, and direction would be j. So, and then, if you plot those, if you plot it, you'll get something like a bunch of things like so again, the idea here is that in most problems, so what am I saying in sum total here is that in most problems, it's easier to calculate the potential V and then derive E from that, if you want the E, by taking the derivative. To get the electric field components. So let me give you guys, another example. So another example. Let's say if we had a ring of charge, a charged ring, okay, and we wanted to get the potential at any point along this axis at the center of the ring. Okay, let's say the ring was of height or of width or sort of radius A, I'm sorry. And let's say there was a total charge of Q on this ring. So that's total charge on ring. And the separation to this point was, say, Z. We would basically look at the increment dq of charge along that ring. And so the incremental unit of charge, so remember what I'm doing here is using this concept that I can calculate, basically if I have a bunch of charges, I can calculate the total potential by summing up the effect of all those charges. Okay, so again, where was I? Here we are. So this sort of the incremental potential, because of this incremental charge, is dq over 4 pi epsilon naught over 1 over z squared plus a squared, which is this distance. Okay. And then the effect of all the charges would be the integral of this dv along, and basically integrating along the circle, and that integral would just give me basically, so the integral of dq over 4 pi epsilon naught 1 over z squared plus a squared along the circle. So this term dq integral would just give me q, because it's all the charges there, over 4 pi epsilon naught 1 over square root of z squared plus a squared. And then from that, so this is the total potential here. And from this, if I want the E field, we just take the derivative of the potential. So again, could be, much simpler to take the derivative of the E field. Okay, so again, in general, it's easier to calculate the potential and then get the E field by taking the derivative of the potential. But, so that's true, again, in most cases, but not in every case. So, especially, in cases where you can use Gauss's law. Okay, so because we're just talking here, we're not talking about physical laws. We're talking about calculation techniques. Okay, so in most cases, as a calculation technique, it's easier to work with potential voltage, with voltage, because you can just do a scalar sum. So you don't have to worry about vector addition. But because Gauss's law is so simple, when you can use Gauss's law, it sort of sometimes makes sense to use Gauss's law, calculate the electric field, because Gauss's law makes the calculation of the electric field so easy. So here's an example of where it might be just easier to calculate the electric field and the voltage. So let's say you had a hollow, get a better circle here. Okay, so let's say we had a hollow conducting sphere of radius r with charge q on the surface. Okay, and then so we want to figure out what the electric field and potential are at any point for this problem. And, here's where it makes sense to use Gauss's law, because we've got a sphere. And basically, if you guys remember, when we had a sphere that's charged up, because the electric field is radial, okay, we can do Gauss's law, so we could draw a sort of any circle around this thing and easily calculate the electric field, because the direction of the electric field is always perpendicular. And given if I have a sort of a sphere around here at any point, the direction of the electric field is perpendicular to that surface, and the value of the electric field is the same along that surface as long as it's a sphere with the center sort of co-located with the sphere. And at any point there, we can just use Gauss's law to get the E field, because it's purely radial. It's the pointing in the radial direction with so all the charge on the surface looks like it's a point charge at the center. So as long as you're outside the sphere, all the charge on the sphere looks like it's a point charge at the center. So if at a point R is bigger than equal to the radius of the sphere, you'd get E sub R Q over 4 pi epsilon naught R squared. So again, because of Gauss's law made life so easy in some particular cases. So from that, we would get, if you wanted to get the potential at any point VR, is we would end up calculating the integral of that from minus infinity to a point R E dot dr. Okay. And basically it gives us, because we define this to be 0, VR is just equal to Q over 2 pi epsilon naught R. Okay. So in this case, ended up being easier to get the electric field first and then get the potential from that. And again, the big difference is, if we are in a situation where we can use Gauss's law, it makes life so easy that it might be just easier to get the electric field and get the potential from it. So if we were gonna do the potential, actually in this case, it would be a more difficult problem, because imagine what we would have to do. We would have to kind of break this into a bunch of like rings, and then figure out the potential from each one of these rings in sort of all directions, etc. So it'd make it'd be actually difficult to get the potential in a case like this, right? But from, because we have Gauss's law, it's so easy to get the electric field, and then we can get the potential from the electric field. By the way, so we said that, the electric field is, this 1 over R squared component, and a point bigger than R. So if you guys remember, if we plot the electric field as a function of R, so I would, this is the radius of the sphere. You would get no electric field. Again, if you guys got to remember, the problem is you get no electric field inside the circle, so the electric field would end up being 0 inside that, and then at the radius you would get a big jump in electric field, and then it would have a 1 over R squared component. And so looking at the potential now, so looking at sort of this outside the sphere, it would have a sort of, I'm going to sort of plot them in the same plot, but obviously they'll have different units and so on. So it'd have a 1 over r sort of component. But note that it doesn't go to 0 when you go inside the circle, but it just stays constant. Okay, so you'd get basically a constant voltage, a constant potential anywhere inside here as you go into the sphere. Because think about what you're doing here in terms of the potential versus the electric field. So again, the electric field goes to 0, but in terms of the potential, you're doing a certain amount of work to bring a charge from infinity closer and closer and closer and closer to the sphere. Now, as you go inside the sphere, you're no longer working against an electric field, it's because there is no electric field inside the sphere, but you're not erasing all the work you did to get the charge from infinity to the surface. So you did all this work to get the charge from infinity to get to the surface, and then as you move towards the sensor, you're adding 0 additional work to get it closer to the surface, but means that this guy the potential doesn't go to 0. It just stays at what it was at the surface of the sphere. So do remember that as an effect. All right. So that was, again, just to reiterate what we talked about. In most cases, it's easier to calculate the potential and then take the derivative to get the electric field. But in some cases, again, those cases all have to do, I think they all, hopefully it's not overgeneralizing that to say that they all have to do with cases that you can use Gauss's law, because it's such a powerful computational tool, that it might be simpler in those cases to take get the electric field, and then from that, get the potential. Okay, guys, so now let's talk about the third topic, about the benefits of using potential or voltage, and that's visualization. Or making, what should we call it, maps? Or, so sort of visualizing how potential looks in space, say. So let's use a quick example, sort of simplified solution, or simplified example. Think about two parallel plates. Trying to use this note-taking tool. Draw a straight line and another straight line. All right. So now let's say we put a bunch of positive charges on the top plate and a bunch of negative charges on the bottom plate. These are conductive plates. And let's say the plates are infinite. So if they are infinite, then basically what you do is, again, given, we've calculated some of these a while ago, what we get is infinite plate had electric field lines going out in both directions. If we think of the charge density, this positive charge density is sigma, then you would end up with, sigma over 2 epsilon naught is the electric field going up, and sigma over 2 epsilon naught is the electric field going down. We calculated this earlier. And then this negative plate also have sigma over 2 epsilon naught. Let's say they have the same charge density, it'd just be the positive charge density here, the negative charge density, but it'd be the same sigma, and it'll affect the direction of the electric field. And so then you'd have electric field pointing in this direction of 2 epsilon naught. Okay, and this is a calculation we did for the electric field of an infinite plate. And the reason we're saying infinite, otherwise it'd be some weird things on the edges of the electric field. But if we call it just infinite, then at every point you'd have electric field pointing like this up and down. And then if you look at the total electric field between the plates, basically, this now adds to this directly. They're all pointed in the same direction between the top plate and the bottom plate. So basically you get these, electric field lines going straight down, and the E field, so you're adding them because the two vectors are pointing in the same direction. And so you'd end up with sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So for the positive charges, negative charges, so you end up with sigma over epsilon naught. Okay, so that's the electric field lines. Now, what would the potential lines look like? So the lines of constant voltage are going to be perpendicular to the electric field lines. So if we were, let me try to draw these a little bit better. So I have these electric field lines that are oops, keep forgetting to do this. Okay. So on. Okay, so the lines of constant voltage are going to be perpendicular to the electric field lines because the electric field lines are pointing straight down, and we call these equipotential lines. So constant voltage lines, equipotential lines. So for example, if we call this voltage 0, you might have this V equal to 1, V equal to 2, voltage 3, 4, and 5 volts here. So basically, if you think of this in analogy with gravity, is you can think of these as stairs you're going up. If this was a gravity, and basically you're looking at G times H. So at any particular height here, again in the gravity analogy, you would have the same G times H. So you would have the same potential energy in a case of gravity. So this is the Earth, and you're going, taking these stairs above the Earth, perpendicular to the direction that the gravity is pointing. So they'd all have the same potential energy. And same with the case of electric potential. If you have the electric field lines all pointing in the same direction down, then these equipotential lines are going to be perpendicular to the electric field lines. And so that's sort of how you think about it. So again, if this voltage here, you call that 0, it'd be 5 volts, and then these equipotential lines would just slice through this electric field lines. So now one thing that's different, so this is kind of a visual of, again, two plates, what the different potential energy lines looks like between these things. Now, one thing that's different between the gravity and electrostatics or electrical case is you don't really have in gravity. You only have positive mass. You never have negative mass. If you had something with a negative mass, then if you put it on the Earth's surface, it would float up, as opposed to get pulled down in towards the Earth. But in the case of electric force or electricity, you do have negatively charged particles, specifically an electron. So if you had an electron here, if you placed it here, it would actually go in this direction, away from the electric field, and so it would actually lose potential energy going in this direction, your electron, and it would speed up. It'd basically pick up. If you dropped an electron here, it would lose potential energy going up to here, and would pick up kinetic energy. So it would start getting accelerating towards this direction. I guess you can think of it as slamming into that plate. Okay, and then it would basically pick up. It would lose. So an electron at an electron between the two plates would lose 1.6 times 10 to the minus 19 joules of potential energy. For each volt change in potential that it would experience. And it would pick up that much kinetic energy. Okay. So, and in fact, there is a definition. So, we said, when you're moving a Coulomb, a volt, you basically get 1 joule of energy. Now that's okay, a good definition. So you talk about in terms of joules when you're talking about coulombs of charge. So, your typical voltages we experience are in the volts or tens of volts or hundreds of volts. So if you're moving coulombs of charge, you can talk about joules, but it's also, a lot of times you're talking about in some experiments, in some areas, you're looking at just one electron. So they have a convenient definition for dealing with the energy of an electron changing its potential. So this is a definition. So, that you don't want to deal with this 1.6 times to the minus 19 joules. So basically they call 1.6 times 10 to the minus 19 joules 1 electron volt. It's 1 EV, and it's pronounced electron volt. So if you take a semiconductor class or something like that, quantum mechanics class or something like that, you start seeing things in terms of electron volts, which is a unit of, the unit of energy, and it's 1.6 times 10 to the minus 19, and it's sort of convenient for that. So for example, let's say you're talking about a hydrogen atom. So hydrogen atom has it has one proton, sitting at the bottom of a well, if I can think of it, that it's sitting down here. So, so this is energy. And so let's say that in quantum mechanically, you're only allowed to work in certain energy states. So don't get too worried about this description. I'm trying to give you guys an example. When you'd use an electron volt, you don't need to remember this or know these quantum mechanical concepts. You guys probably are aware of that you can have only some finite energy levels. But what's so-called the ground state, the lowest state that an electron can have, is at minus 13.6 electron volts. Okay, and then so it means that you have, if you want to liberate the electron, if you want to basically get that electron in your hydrogen atom, if you want to ionize that hydrogen atom and you want to shoot off the electron away, you got to do 13.6 times 1.6 times 10 to the minus 19 joules of work. You have to put that much work to 1.6 times 1.6 times 10 to the minus 19 joules of work to remove electron from ground state in a hydrogen atom. And again, this is this unit of electron volt that again you guys may have seen if you've taken semiconductor classes or dealing with quantum mechanics. It's just a convenient unit of energy, convenient definition when you're talking about individual electrons, etc. Okay. All right. So anyway, so that was sort of sorry about that tangent. Now back to what we talked about. This visualization of equipotential lines kind of allows you to see how sort of the potential energy that you would have in space. Okay, so for example, let's use another example. So another example is a point charge that we've looked at a lot. And so it would have, these radial electric field lines. So this is a point charge plus Q at the center. Has these radial lines coming out. So again, if you wanted to plot the equipotential lines, they would be they'd be perpendicular to the electric field lines. So equipotential lines would kind of look like this. And so everybody in this would have the same potential. And then everybody on this would be at the same potential. Again, these are perpendicular surfaces to the electric field lines. So they're equipotential lines. And then they drop off, the potential drops off as 1 over R as you move away from point charge. Okay. Let's think of yet another example. So dipole example. So of the axis of the plus Q and the minus Q, and you would have these electric field lines between them. Like that. So the equipotential lines here, when you're looking very close to one of the charges, say looking at the very close to the positive charge, it almost, you can kind of almost ignore the negative charge, so it looks like a point charge. So equipotential lines would be circles here, but as you move away, they would start getting all distorted. And then so on and so forth. And then same here. And then sort of, as you'll see, importantly, when you're right at this x-axis, it'll just be a plane, the equipotential line just at an x-axis. So it just turns at x equal to 0, the equipotential line turns into a plane. Okay, so again, they're called equipotential lines, and they're always perpendicular to the electric field lines.